All right, in this supplement video, we're going to look at the big topic that got removed from the APs. And there's actually two topics, but I'm only going to really look at this one. It's about using something called a chi-squared distribution. And there's two kinds of tests you can do with a chi-squared distribution. They're from the course. One is called a goodness of fit test. There's actually three types of tests, but the other two are sort of the same exact test. So the first one's the goodness of fit. The other two are called a test for independence and a test for homogeneity, but they're really the same test. I'll tell you in the next video why they go by different names, but there's really just two techniques. All right, so we'll look at these chi-square curves because they come up and they're important, and some of you who maybe have taken AP biology or something have run into them. So I figure it's good to go over because it appears in other stuff. Basically, this is all we'll look at. There's another topic that had to do with doing these like tests on slopes of best fit lines, but it's such kind of an oddball topic, I'm going to leave it out. So we'll look at these chi-square tests, and that should make 3 lessons, and that'll round out the next 3 weeks, and then we'll be done. All right, so this would have been our last unit on what I call other inference techniques. So the first goal is to perform what's called a chi-squared goodness of fit test. And I don't know how the goodness of English of that, but that's what it's called. It's called a goodness of fit. So we'll talk about what this is. And the chi-squared tests basically work with many values because we looked at like one mean and one proportion and two means and two proportions. The chi-squared tests work with many numbers. So usually you have either a list of values or a table of values. All right, so for this goodness of fit test, it's going to be a list of values, and then the next two that are really one lesson are a table of values. All right, but basically it comes down to this other distribution, something called the chi-squared curve. The chi-square curve is got an interesting shape. We'd talk more about if we had more time, but basically it's based on the normal curve. If the normal curve distribution gets squared, it forms this thing called a chi-squared distribution. So I'll show you what it is and how to use it. You don't need to know the real details of it. Just realize it exists, and this is one of the ways it gets used. All right. So let's dive into this chi-squared goodness of fit test. All right. So it's always good to have the motivating example. That's what I always try to do in statistics. It gives you an idea what's going on. So here's an example about the zodiac. So the example says, does the zodiac sign predict business success? The top 400 companies are, I guess they're sampling, they get information from 256 of them. So of the top 400 companies, 256 of their head officers report their zodiac sign, and below is the table of values. So I abbreviated the zodiac signs, but in order. They usually start with Aries. I'm an Aries. Starts late. I think it's late March into early April as Aries, and that's the first sign. And then there's Taurus and Gemini and Cancer and so on. You go all the way up till you get to Pisces. So if you know anything about the zodiac, those are the 12 zodiac signs. They're split evenly throughout the year. Now, when we look at the values, though, some zodiac signs have more people in them than others. So for example, Gemini only has 18 people. Pisces has 29 people. So the question here is, because Pisces has more, does this mean that it's the zodiac sign or some relation to that, right? Are Pisces just more likely to be successful in business? That's what your horoscope might tell you. So, in fact, the difference is kind of like there's 29 here, and like I said, only 18 in Gemini and 18 in Libra. So what we want to know from a chi-squared test is this has a certain distribution. We're going to look at its expected distribution if the zodiac sign doesn't matter. So basically it's like a null hypothesis. If all things were equal and the zodiac sign had no effect, the overall expectation is that that the people should be evenly distributed through the zodiac sign, right? If it was all things being equal and it was perfect or it was done over and over again, if the zodiac sign really has no effect, they should be evenly distributed. Now, we're seeing that they're not evenly distributed. But however, remember that in statistics, natural variation always comes in. So what we really want to know here is the reason Pisces higher because it's actually got something to do with the zodiac, or is Pisces just higher because this is a random sample and there was some natural variation? And of course, it would be very odd if everyone actually was equal, right? That'd be kind of strange. Because even if you're evenly picking people, there's going to be a little bit of randomness, and you're going to get more of one type than another, even if they are overall evenly distributed. So that's what, like most things in statistics, that's the question this is going to answer. We took a sample. The sample has some variation in it. We want to see, is this variation enough to show that the zodiac sign is somehow related to the higher numbers? Or are these numbers, is it possible that the zodiac sign has nothing to do with it, and these numbers just came out the way they were, regardless of the zodiac sign? All right, so that's sort of what we're trying to figure out here, or I should say sort of, it's exactly what we're trying to figure out, is do we think this is supporting the zodiac sign, making people successful, or is it not strong evidence that the zodiac sign, or maybe it's not evidence at all that the zodiac sign has any effect? All right, we do see variation, but as usual, is the variation due to just natural randomness, or is it varying because there's really a pattern, that there's a strong proclivity toward Pisces or whatever? All right, so how do we answer this? Well, the first thing we would want to do is figure out, even though these are the values we have, what are the expected values? So we need to come up with some hypotheses about what we think should happen if the zodiac doesn't matter, and then our alternative would be what would happen if the zodiac did matter. So basically, doing this is going to be like a hypothesis test, basically. In fact, it has the same steps and everything. So we're going to treat this like a hypothesis test. Our null is going to be the normal state of affairs. So what would be normal is that the zodiac has no effect, and things would just be randomly distributed, or evenly distributed. So our null would assume the zodiac had no effect. If for some reason we could show that the null isn't likely true, then the alternative would be that the data shows that there is some effect present. So when you do chi-squared tests, null hypothesis and alternative hypothesis, when you do the hypotheses, you put them in words, because it's a little annoying to go Aries would equal Taurus, would equal Gemini, would equal whatever. So what we're going to do is say it in words. The null hypothesis is, we're going to assume if the zodiac has no effect, that in general, the births should be uniformly distributed over the zodiac, right? So if the zodiac has no effect, in theory, we would think that the CEO of a top business would be equally likely to be any of the zodiac signs. It doesn't mean we would get equal representation, but it means in theory they would be, you're not more likely because you're Pisces or because you're Aries to be more successful. So we're going to assume the births are uniformly distributed over the zodiac. If for some reason we have evidence that the null is not true, we'll go with the alternative. The alternative would be the opposite, that the births aren't uniformly distributed over the zodiac, meaning that some zodiac signs actually have more success than other zodiac signs, in which case we might be able to say, well, Pisces was the highest. Well, maybe Pisces are more successful in business, right? Like your horoscope said or whatever. So this is going to be the null hypothesis, the normal state of affairs, is that the births are normally distributed. If that's not true, we'll seem to think that, well, for some reason the births are clustering around certain zodiac signs. It doesn't prove causation, but at least goes, well, zodiac sign has something to do with it for whatever reason. All right? So those are our hypotheses. So we need what are called this thing never works right. We need what are called the expected numbers. So what if the null hypothesis were true, what would it mean? Well, mathematically speaking, the null hypothesis would mean, what would we expect? We'd expect that of those 256 people that were sampled, they should in theory be split 12 ways, right? If there's nothing to do with the zodiac sign, we would take the 256, divide by 12, and if we actually do that, 256 divided 12 is 21.3 repeating. So in theory, once again, it's theoretical, we expect 21.3 repeating, or 21 1/3 people in each category. Now, obviously, it's not possible to have 21 1/3 in each category. And once again, we also expect some natural variation. It's even if it was perfect, when we took a sample, we might get lucky and get one type over another by just random chance. So even though mathematically this is the expectation, we have to consider this. We wouldn't expect the sample to actually match the null. Even if the null were true, our sample, it'd be very rare to get a sample that was perfectly dead on. In fact, in this case, we can't actually get a sample because we can't get 21 1/3 people, right? We'd have to either get 21 or 22. So it's actually impossible to match perfectly the null. But since we don't expect the sample to actually match the null, since some deviation is natural. So it's okay to get some deviation and the null could still be true. So that's what this chi-square test is going to do. If the deviation is large enough, though, if we get like extreme deviation, that seems to suggest the null's not true. So like, say I picked a random sample of CEOs and everyone was Pisces. Every single one of them was Pisces. It would be hard to say, oh, well, the zodiac sign had nothing to do with it when everybody who was successful was in Pisces and nobody was in any other category. So we allow a little bit of deviation, but there's a cutoff where too much deviation seems to point to the fact the null's not true. So that's what the chi-square test is going to be. It's going to tell us how much deviation can we have before the sample's so deviant that it seems to contradict the null. So we expect 21.3 repeating people in each category. They're a little off. It's not enough to question the null. If it's far off, it questions the null. So then how do we test all this? Well, this thing goes on. We're going to use this thing called the chi-square distribution, and here's roughly what a chi-square curve looks like. The important thing is just to realize it's a probability distribution, kind of like a normal curve. The area under this curve is 1, and the way this gets used is it measures the likelihood of deviation. Now, there's different looking chi-square curves. Chi-square curves, just like T-curves, they have degrees of freedom, so I'll show you what different ones look like. But pretty much almost every chi-square curve has this shape to it. It comes up with a big lump and then it has this trail off to the right. So they're all skewed to the right. Basically what it does is we're going to measure the deviation. So we have our null model, and then we're going to start measuring, well, the actual sample we took deviates a bit from the null model. If it doesn't, these are the probabilities of a certain amount of deviation given the null is true. So actually, given the null is true, we don't expect something that's dead on. There's very low probability that it actually matches the null exactly. Some deviation's expected. This is where we come into this range, right? If there's some deviation, that's allowed and that's consistent with the null model. If the deviation gets too far, the probability of going out here becomes less and less and less. Like I said, because if we start doing values, that be out here, there's very little probability that you're going to be like, this happens to be marked at 16. It's very low probability you're going to get something at 16. So the farther you are out here, the less likely, because this is basically what would happen with the null model. If you're in here, it's likely the null is true, or at least we don't question the null. If you start deviating too much, it starts to become less and less likely. And then if it's really unlikely to have high deviation, that probably means the null isn't true. So basically, we're going to get a p-value like we did last time based on this deviance number. Now, I keep saying we need to measure the deviance, but how do we do it? The good news is the calculator will do it for us. I'll talk about how you make the calculation, but overall, I'll show you how to do it by hand, like just for one example, and then after that, you can just have the calculator do it, just so you know what the calculator is doing for you. All right, but basically, this is the new distribution we're going to use. So when we do a test, we're still going to get p-value. We're going to get p-value by basically finding how much area we've taken up of this curve, basically how much is left over. So if it's we're still going to have the cutoff of 0.05. We're basically going to measure wherever we are out further. So if we're at 8, we would measure how much probability. So if we're here, there's a lot of probability it'll happen. If we're out here, there's not very much probability. And if we go under 5% or we go over our, we go under our cutoff value, then we reject the null. So it's just like before, just as a different curve to do this on. So let me show you how this will work. And let's look at the different chi-square curves. Chi-square curves have different degrees of freedom. So because depending on how many categories you have, the more categories you have, the more deviation you're going to allow in each cell, right? You have 12 different categories here. Each one can vary a little bit, and that adds up. So the chi-square curves are based on something called degrees of freedom, which is n minus 1. Since we have n's our number of our sample or categories, I should say, because the sample is 256. It's the number of categories we have. So since we have 12 categories, we do 12 minus 1, we have 11 degrees of freedom. The calculator will generate a chi-square curve. So the higher degrees of freedom, the more this chi-square curve stretched out. Chi-square curves with 1 or 2 degrees of freedom actually they don't have enough time to make this like lump. They just kind of drop down. But once you hit 3 degrees of freedom or higher, it basically makes the shape where there's this lump and then it's skewed right. And the more degrees of freedom, the more stretched out it is, but it still has that shape. Basically, this thing like has the lump, but it still is skewed right, even though this has 10 degrees of freedom. So basically, the more categories you have, the more deviation you're allowing. So if you have 3 degrees of freedom, you don't want to allow them, if the deviation is 10, that's a lot. But if you have 10 degrees of freedom, a deviation of 10 is not that much. All right. So basically, you need to pick the right chi-square curve. You do it by however many categories you have. So in our case, we have 12 categories. If you had 20 categories, you'd use 19 degrees of freedom. If you had 3 categories, you'd use 2 degrees of freedom, and so on. All right, so we're going to use 11 degrees of freedom. So we would need to make a chi-square curve, or the calculator will do it, and then that's where we'll test our deviance value. So when I was showing you this, this chi-square curve, this is probably a low number of degrees of freedom. So the one we're going to use is going to be a little more stretched out. So if our deviance gets to be too high, it'll reject our null. But if the deviance isn't too high, it's consistent with the fact they were evenly distributed. That's basically how it works. All right. So here's the idea. The chi-square curve, or this chi-square test, will measure deviation. It'll tell us, are we close to our null model, or is there too much deviation to be close to our null model? It doesn't tell us the intensity of the deviation. So for our example, it says if we find zodiac affects business, the chi-square curve doesn't tell us, or chi-square test doesn't tell us which zodiac sign is causing the imbalance, right? So if we look at the numbers, it looks like Pisces is high, and like I said, Gemini was low. But the test won't tell us which category is high and which category is low, or if several categories are high and several are low. All it will do is tell us that there is deviation. So it'll just tell us, yes, this could have come from your null model, or no, there's too much deviation. But it won't tell us specifically where that deviation comes from, all right? So it won't tell us which specific zodiac sign is causing the imbalance or by how much, just that it's not consistent with the null model. So how do we measure the deviance? This is the part that I will show you on 1 or 2 examples, but overall the calculator will do this for you. So in order to get the deviance number for the chi-square goodness of fit test, we're going to get this thing called this chi-square statistic. So I don't know if I mentioned it before. Let me see if it's on the picture. Yes, I forgot to talk about this. The symbol for chi-squared, because chi is a Greek letter. I mean, some people might call it chi or chai or whatever. You hear different pronunciations. But in statistics, they call it chi. So chi is a Greek letter, and it kind of looks like an X. It's like a squiggly X. So the chi-square curve is that Greek letter chi with a squared on it. So if you see that curly X symbol in statistics, it's representing this distribution. All right, so how do you get that number to test on the chi-square curve, basically how far you go out? You can get that number by doing this. So what we're going to do is use, for each one of our values, we have an observed value and an expected value. The observed value is what that table I listed. There are 12 observed values. The expected value I mentioned was 21.33, right? If the null model is true and really everyone's evenly distributed, in theory, we should get 21.33 people. So that's the expected number. So what you do is, for each cell, so if you were to do this by hand, you'd have to do it 12 times. You'd have to take the observed value in the cell, subtract the expected value, square it, divide the expected value. You would get a number, and then you would do that for every cell. So you'd have to do a lot of calculation. You do that 12 times, add up all the cells. Remember, this means to add. So if you add up all the cells doing this calculation, it gives you the amount of deviance. The good news is the calculator will do it for you. So basically what this says is for each cell, and basically I just explained, for each cell we'll take the observed value and the expected value and use this to calculate a number. We add up all the numbers we calculate, and then that's our measurement of deviance. And basically, if you think about it, it does measure the deviance. It says how far away, here's your observed value, subtract the expected, tells you how far away they are, and then it squares it and divides it. So it sort of rescales it. But you add those up, and every time, because basically the farther these are apart, the bigger this value comes out. So if something's really far off, it adds in a lot of deviance. If it's really close, or if they were exactly on, you would get 0. So this thing measures the deviance in each category and then adds them up to give a total deviance. That we test with the chi-square curve. If the deviance is within tolerance, we go, okay, well, the null's probably true, or at least we're not questioning the null. If the deviance adds up to be too much, well, then we sort of go, well, the null doesn't seem like it's true because we've got way more deviance than we would normally see, all right? So let's look at calculating that, but beforehand, because I want to do a test, remember there are conditions as well, so for every test there's conditions you got to check. The conditions are pretty easy to check because the first one is something called counted data condition. Basically, we're not actually working with proportions or means like we were before. We're working with what are called counts. So you need to make sure your data are counts, that someone just counted up a number of things. If you have proportions or percentages or measurements, you can't do the chi-square test. It has to be counts of a category. All right, so make sure your data is counted. In our case, we did. We counted the number of people in each zodiac sign. So in this case, it works. So we have our counted data condition met. Independence is always the case. You need to make sure that one cell doesn't affect another. Well, basically, I'm Aries. If I become a CEO, it doesn't affect somebody else who's Taurus becoming CEO or something, right? So we could say that the cells are independent. Once again, randomness is necessary or else we get bias. So you need to make sure that the people were randomly picked. Or that they're at least representative. I would say it would sound like of the top 400 CEOs, they did get them to select themselves. But we'll still say, since it's 256 of them, it's reasonable that they're reasonable representatives of the leaders of successful companies. So they need to at least be representative of the population. We'll assume that this sample is, though it might have helped if they, we don't know if they randomly picked them. Sounds like they picked themselves, but the last condition is to check this thing called the expected cell frequency condition. So basically, you always need that condition when you have enough information. Each cell has to have an expected value of at least 5. Beware that the cell doesn't actually have to have 5 members, but if your expected value is under 5, once again, the test, it's kind of too small of a sampling to work. So make sure that the expected value of each cell comes out greater than 5. Now, our expected value for every category is 21.33, so we meet the condition. All right? So finally, how do you conduct one of these tests? Well, first, let me show you how you get the deviance number, because like I said, I'm going to show you at least how to do 1 or 2 of the cells, and then the rest will be done in a calculator. So let's look at first how we get this deviance number, and then once we see how to get the deviance number, I'll show you the test in the calculator. And the calculator pretty much does all the work. So how do you get this deviance number, this chi-squared, or how will the calculator get it? Because once again, the calculator will do it for you, but it's good for you to at least know what happened. I'll just do it for the first 2 numbers. So here's our table of values, not the entire thing, but I don't want to write it all out because I was going to do it all. But here's, Aries, Taurus, Gemini, Cancer. And we can keep going, Leo, Virgo, blah, 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 all the way up to Pisces. All right. So if I were to do it by hand, I would have to follow that formula. And so I show it being done twice. If I do it for Aries, I would need to take the observed value minus the expected value, square it, divide by the expected value. I have in this table here all the observed values. If the null is true, here's all the expected values, right? So 23 is not that deviant from 21, but 18 is a little more deviant, right? And so on. The good thing about squaring is it doesn't matter if the deviation is positive or negative. By squaring it, it'll get rid of it. Because in the first case, this value is positive, but in the second case, it comes out negative. But by squaring it, the answer will always be positive. So if you follow this formula, basically what you would do if you were doing it by hand is do it for each of the 12 categories. You'd put in the observed value, subtract the expected value, square it, divide by the expected value, figure out what that number is. So the first deviance number is 0.13075. The torus deviance number is a little less because 20 is closer to the expected value than 23 is. It's on the other side, but once again, it won't come out negative due to that squared. So the deviance for torus is small. It's 0.08293. Then I would do it for Gemini, and I didn't do it because I don't feel like doing it over and over again because the calculator will do it for me. So Gemini, you would do this. Cancer, you would do this. Leo, you'd do it, and you'd do it all the way until you got up to Pisces. Once you got up to Pisces, you'd be like, okay, I don't need to do this anymore. In the end, once you get these 12 numbers, you would add them all up, and you get the chi-square test statistic is what that's called. So that's what you put on the chi-square curve. And then you test that. So now I'm going to show you how the calculator does the rest for us. So let's actually look at the test now. So now that I've talked about that part, how do we do the test? Well, that's on the next board here. So let me put up the next board. And let's see how it goes. So here's, I won't say the full test, but pretty darn close to it. So the top are my hypotheses. I already showed them to you. So if I was doing the full chi-square test, I would go, well, I want to see if the zodiac is affecting success in business or chance of being a CEO or whatever. So I'm going to assume that in my know that the birds are uniformly distributed over the zodiac. My alternative is if that ain't true, then I'm going to think that birds aren't uniformly distributed over the zodiac, meaning the zodiac has some kind of effect on people's success. So I have my hypothesis set up. Number 2 is to do the conditions check. I already did them verbally with you, so I haven't checked off. The counted data, it's counted data. We said it was independent. This one, I wasn't quite sure if it was random, but it seems like it's representative, so we'll just trust them. And then the expected cell frequency. Remember, the expected cell frequency needs to be 5. It doesn't mean the categories have to be. So if the actual values were less than 5, that's okay. The expected values have to be greater than 5. Since they're all 21.33, we're good. So now this part, how do you figure out this stuff? Well, I have a picture of a chi-square curve. And where do I get this chi-square statistic from? The deviance adds up to 5.0938. So those numbers I was getting, that's what they add up to. How do you get the calculator to do it for you? Well, all you have to do is enter the 2 lists. So if you go to list, like we always did, and edit, so you go to stat, remember, go to stat and go to edit, and you can edit the lists. I put in the list. You have to put in both lists. So the first list, typically, if you want to make it easy on yourself, you put in the observed values. So these are the actual values that our sample came up with in their distribution all the way to Pisces, which remember had the most, 29. You have to put in the the observed values and then the expected values. Now, the expected values don't have to all be equal, but in this example they are. So in another video I can do one where they're not all equally distributed. But in this case, I'm going to make it easy, and they're, we said we're expecting them to be distributed this way, 21.333. And I put that in for every single second list. So now that I have all the observed values and all of the expected values, make sure you can see it. So now I have all the observed and expected values. Now what you do is you go into where all the tests are. So you go into stat, you go over to tests, and you scroll down quite a ways. So I'm showing that off screen, but I had to go all the way down to D. You'll see it, chi-squared GOF. That stands for chi-squared goodness of fit test. So what you do is you hit that, and it asks you to put in the lists. Now, if you picked different lists, you'd have to go select them, but I put my observed values in list 1, and I put my expected values in list 2. The only thing you'll have to do is put in the degrees of freedom, because that way it makes the right chi-square curve. Remember, degrees of freedom with the categories -1. So if I had 15 categories, I used 14. Since I had 12 categories, I used 11. So now I'm going to go down to calculate. And I'll show you draw. Draw makes the picture. But if I go down to calculate, it will give me two things. It'll give me the chi-square test statistic. So it'll tell me what all the deviance added up to. And then it'll tell me what's the probability that that kind of deviance happens. Basically, what's the probability I get this or rare? Well, notice the p-value is pretty high. So now I'll go back to the board. Those are the two things you want to show. And here, I'll show the picture of the chi-square curve. Give me a second to go back in and do this test again. So I'm just going to go to just show you where I didn't really get the picture from there. I just kind of made it up myself, but I'll show you how you could get the picture. If you go back to the chi-square goodness of fit test and go over to draw, it'll show you, it'll make the chi-square curve. Well, it's not showing it very well. Let me see if I zoom. Oh, there it goes. Okay, sorry, I had something else in. So ignore these other lines. This is, I just made the calculus video with it, and I accidentally left those other functions in there. So notice it makes the chi-square curve, and it put the value of deviance and goes, what's the chance I get that much deviance from this or more? Well, it's pretty likely to get this. This isn't a very unlikely result, so it's consistent with the null. So notice it gave me the p-value, which is high. So because it's way down here, there's not that much deviance, and it's consistent with the null. If it was way out here, I'd get a very low p-value, and I would reject. Well, the p-value is high, right? So my cutoff is 0.05. My p-value is huge. My p-value is 0.9265. So remember what we do in the case of a high p-value. We don't reject the null. So basically, because this p-value is high, so it says due to high p-value, I will fail to reject the null. What does that mean? Hopefully you can read the whole thing there. What it means is I'm not going to question the null, meaning I think the birds are uniformly distributed. So I go do the high p-value, we fail to reject the null. It means it's reasonable to believe the birds are actually distributed evenly across the zodiac signs. So what does that mean? That means that the zodiac probably isn't affecting things, right? It's very possible that Pisces was a little high, Gemini was a little low, but it could have come from basically if the population was evenly distributed and we randomly selected, we could have gotten one that was this deviant. It's not so deviant that I'm thinking the zodiac has an effect. So that Pisces seems a little high and the Gemini seems a little low, but they're not really unusually high or unusually low. So basically what I said was the birds are probably, or it's believable that they're evenly distributed across the zodiac, so success is probably not based on zodiac sign. Pisces is high probably due to natural variation, not due to the fact that Pisces is actually making people better at business. All right. Keep in mind with these tests, there's always the chance of error. So I'm basically saying the zodiac sign doesn't seem like it works. I could be wrong, right? It's possible that I just got a sample that wasn't that deviant and the zodiac sign actually is working, but I don't have evidence for it. So beware that you could still make type 1 and type 2 errors doing this. But overall, the p-value is so high, it's very unlikely I'm wrong in this case. So that's our conclusion. Now, just because I'm just doing one example, because these take a while, I'm already at 34 minutes. That's why you're only doing one a week. The p-value, say it was low, so say the deviance, so let me give you an example of how it would go the other way. Say Pisces was way higher, like say Pisces had 100 people in it, and the other ones were really low. Or maybe Pisces and Sagittarius were really high, and the other ones were low. Well, what would happen is if they were significantly off from the null, right? Like there's 100 people in Pisces and 100 people in Sagittarius, and all the other ones had like 3 people or something. What would happen would be is this deviance number would be way higher. So what it would cause that chi-square statistic to go up this number would move way down here. And what that would say is it's easy to get this 5 deviance. It's not easy to get deviance down here. If the deviance were really high, it would be down here. It would make this p-value low, and it would reject the null. So basically, if the value is moved here, the p-value would be very low. And then we'd go with the other one. We'd say basically, well, it doesn't seem like the birds are uniformly distributed. It seems like they're really clustered somewhere. Once again, we'd have to look to see where, but the low p-value would make us reject the null. If we rejected the null, we would go with the alternative, which is that the zodiac seems to be affecting the birds. All right. So anyway, that's more than enough. The example I gave, so I gave just one problem. It's, I think I actually have the numbers listed on here. So you'll see some kind of numbers like this. It's out of the book. But basically what they did, just to explain to you really fast, is they looked at the digits of pi, and they went really far out on pi, and they counted how many times they saw each digit. So they counted these, and I'm trying to remember, I think they went out 1,000,000 digits, I think, yeah, from this. They go out 1,000,000 digits, and they count how many times they see each digit. So we'll probably use a computer program to do that. But notice that they're not completely evenly distributed, right? Like 0 shows up less than the number 2. But once again, is this natural variation? Is pi overall evenly distributing the numbers, or is it favoring one of the numbers? So you can figure that out in your example. It's very similar. You can just figure out what are the expected values, throw this list in the calculator, do the chi-square test, and just see how the p-value comes out. All right. So this you'll see in the exercise to see if you can do it yourself. Basically, there's this, and then there's one more chi-square test. So this is so long because I had to explain about chi-squared, but the next one will be a lot faster because once you know the distribution, we can just go through the modification to the test, and then that'll be it. We'll be done. All right. So sorry, I didn't mean this to be this long, but it'll be your only one for the week. All right. So do the assignment, and until next time, stay safe.